Okay, so in this video, we will begin to tackle all about exponential search. So when we say exponential search, that is also known as a doubling search, galloping search, or finger search. It is a search designed for efficiently finding a target value in a sorted array or list, especially when the list is unbounded or its size is unknown. So it was introduced by John Bentley and Andrew Chiao in 1976, and it combines the concept of rapidly finding a range where the target might exist, the the exponential search, then followed by a binary search within that range. It is especially efficient when the element you are looking for is near the beginning of the array. So in this case, Les, for example, you have 10 specific elements in your array. Then in exponential search, you will begin to multiply that in itself actually. So say for example, multiply that by 2. So I mean because in exponential, you will begin to, for example, you're at a zero right now, search zero, search one, one times two, it will become two times two, four, it will become four times because eight times two, 16. So that's how you will deal with that later on. So after, for example, when you will jump to 16, then you're actually now at from 8, you jump out to 16 index. And afterwards, the element or the target is absolutely in the middle between 8 and 16. So therefore, what you have to do, you have to go back um, to the previews and we'll do the binary search within that range from 8 to 16. So that's how you will deal with that. So it will eventually apply the binary search afterwards. So in exponential search, the steps for that, you have to check the first element. For checking the element, if the target is at the first position in that's zero, if the element you're looking for is at array zero, zero and exit target has been found. So immediately that is the best case if you're able to search that in that certain matter. Now afterwards exponentially increase the search range. Start from index one. After the index one, you have to double it. Double the index at each step. Like go from 1 to 4, 8, 16, etc. So from 1 times mo siya, 2 will become times 2, 4 times 2, 8, as what I mentioned. At each step, check if that array or if that index or what element in that specific index right now, if it is greater than or equals to the target, you have to go back into the previous and we'll do the binary search. If the current element is greater than or equals to the target, stop doubling and move to the next step. So if the current element is greater than or equals to your target, you have to proceed with the next step accordingly. Now you know that the target element lies between the previous and current indexes, so you will be going to perform the next step, which will be the binary search already. So perform the binary search in this one, as what I mentioned to you. After finding the range where the target is between two indices, say array previous index and current index. So that will be the basis. Since in our binary search, you have to declare where is the previous, I mean the low index as well as the high index, and you will begin to divide it into two, and what will be your element that you can find. That is how it works. So you have to perform a binary search between those two indices. Binary search will efficiently search within a bigger range to find the exact position of the target element. Afterwards, you have to return the index or not found. If binary search finds the target element, return its index. If the binary search doesn't find the target, return -1, indicating that the target element is not in the array. So if you were able to find the element, found the element in any given position, so you can definitely easily retain the value of that particular index. And then you must mention that it was found in index 3, for example, or whatever, depends on you. Then if we're not able to found after a thorough searching, you just have to easily declare that it is negative one. So for the time complexity of this one, it is a combination of two steps, exponentially finding the range where the element might be, and binary searching within that range to find the target element. So in the best case in here, accordingly, that is a constant time because it occurs when the target element is found immediately during the range finding phase. This happens when the target is located at the first index, like 0 index. So say, for example, if your array is 0, if it is equal to your target, definitely that is the best case currently. Now, afterwards, the average case will be the annotation of logarithmic of I, which the element is found at position given I times depend on logarithmically on I. What should I say I? That is your indices. Worst case as well, a logarithmic event. If the element is not the end or not found, the search touches almost the whole array, depending logarithmically on the total size. And so you were able to exhaust a lot of things or a procedure. It will be taking a lot of time. There will be a lot of checking steps that you were able to do. And for the space complexity, it is a constant time because it will only use a few variables and no extra memory proportional to the input size is required. So you were not able to utilize a lot of space in here. So that is the exponential search, and I hope so that it is clear, and I will begin to illustrate that in the next video as well. So see you in there.